Hello, my name is Henrietta Dombrovskaya, and today we will be talking about implementing of temporal features in PostgreSQL, SQL Standard, and beyond. So, who am I? As I already said, my name is Hetty, and currently I am a database architect at DRW Holdings in Chicago, Illinois. My other important job is local organizer of Chicago PostgreSQL user group, and I'm very proud of this job and contribution I make to Postgres community this way. And also you can see me speaking and participating in many Postgres conferences all over the world. So, without further ado, let's get to the point. Let's get to the temporal database basics. The concept of storing time with databases had been popular for a very long time, pretty much since relational databases come to life. So there were many theoretical works, many models, and they were mostly theoretical. People tried to implement it, it not always worked. Last year, however, that was kind of a breakthrough because it was not a breakthrough, but there was a word because last year at Postgres Vision 2022, Mike Stonebreaker, in his keynote, listed 4 things he wanted to see in Postgres, and first thing was time travel. And then everybody actually started to call me, Hetty, did he talk to you? No, he did not, but I'm very happy that this topic came to life again, and I can talk about it, and now people are interested again. So let's see what we want when we say we want time travel. What are the types of queries? What are types of information we want to obtain using temporal databases? First is point in time or snapshot queries. Something like how my report looked like last day of the previous month. And I do not mean parameters. Okay, I have this report, I ran it with the same parameters today as a month ago, and it looks differently. So can I actually go back in time and run it as it? So those are snapshot queries. The second type is change log. So I have my request and it got changed overnight. It looks differently when it was changed, what it was before, how it was changed. I want to go to change log and see what happened with it. And the third type is most difficult and most underdeveloped are the fully temporal queries, fully temporal joins. So when these two objects coexisted, or something like, okay, who was a head of QA department when Mike Smith started to work in QA department, and all these other temporal correlated queries. These queries use predicates like before, between, meets, after, and all these temporal predicates. And the result of this query may be another temporal relation. So we do not join the values and see the result, but we also see at different times, we can actually have different results of these joins. So that's all interesting, but that's all theory so far. So then how we can do it? So though there were more theoretical papers than practical implementations, even in theoretical papers, people try to kind of decide, figure out how it can be implemented. And every theoretical paper starts with snapshots. So basically what it means, the moment something changes the database, we create a full copy, we create a snapshot of this database and going on and on. Very theoretical, not very practical. The other way to implement a potential solution is event log. Everybody loves event log. So you have application, you go to your manager, you say, we need to record everything for auditing purposes. They're like, go for it. So hopefully somebody at some point will analyze it, will be able to figure out they preserve the information, they are very inconvenient to use. And then people who actually try to implement temporal data, temporal queries, they use periods. So for each record or for each value, they assign a period of time when this was valid, when we believe it was true. So all these three approaches are equivalent in some sense. like theoretically, but the actual query performance obviously differs dramatically depending which path you want to choose. Now let's talk about time dimensions. Time dimension is something which is like absolutely counterintuitive, something you like do not think in real life. Okay, in real life, time is the fourth dimension, right? Why we have dimensions of time. But the moment you start to implement time, you see that you need to tell what time we're talking about. And most times people distinguish at least three dimensions, at least two dimensions. Okay, so first is transactional or system time. There's the time when something was recorded to the database. Then valid time, also called effective time, that is something which we say we believe these values were true, these values actually existed, they were like actually effective. And asserted time is something a little bit more complicated. It's kind of transactional time, but not exactly, and way less systems use it. And actually, there are lots of other time dimensions which were explored and people try to implement it, but they're like way less popular than these three, actually. Now, let's look at the standard. So we have SQL, we have SQL standard. And there were several attempts to standardize these ideas, what we want from temporal relational databases. Several attempts, like one which started in 1996, I think, actually was abandoned in 2001. It like never came to life. And finally, the complete ANSI SQL standard, which included temporal tables, was developed in 2011. And that's what we use since then. So what we have in standard? A standard, interestingly, does not introduce the period type. And the reason was because people did not want to demand having the period. The idea was, if you already have database, if we will introduce new type, if we request the new type, then you need to change here and there how parameters can be. So you need to change allowed values for functions, procedures, and too much work. So basically what they said, okay, so you can have one time stamp is the period start, one time stamp is a period end, and any time period is defined as closed open. So the start is included, end is excluded. Also, standard supports all these time predicates, overlap, meets, like all the others, not exactly as alien relationships, alien predicates. We won't go into this. There are some differences, but they're clearly defined in the standard. And then standard defines two time dimensions, which it supports at a minimum. One is the system time, that's the same as transaction time, and the other is application time, which is sometimes called valid time. So what we can tell about system time? First of all, standard says that this name is fixed. So if you have any table by the standard where you have system time, it should be called system underscore time. And it always can be before and now and can never go to the future. So the idea is that we record actual time, and once it's recorded, it can never be changed. So just stuck with these records, with these values, and lives forever. In contrast to popular beliefs, standard does not require having separate historical table and separate current table. The thing is that standard treats current record differently. So kind of current is our current main version. And if we run a query without specifying system time, it's assumed that we run it on current time. But by no means standard requires that current goes in one table and all the rest goes in the other. Whoever implements it this way, it's like implementation details, not the standard details. For application time, standard actually just says that it is maintained by the user. So standard does not really put any restrictions on the application time. Column names can be whatever. And again, the idea is if you already have a database where you did your custom implementation of application time, you can use your existing columns. So the thing is, you define it as an application time when you define the table. And right now since 2011, standard defines only one application time, though it leaves the room to increase it in the future and have more than one application time. So primary keys, it's kind of like, so standard does not really define clearly what is the primary key for temporal tables, doesn't provide clear resolution. Because if you think, okay, we have an actual primary key and then we have period start, period end, these three together should be a primary key for the temporal table. But no, and you know why? Look at this example. So here, technically speaking, these two records have unique combination of three elements, but these records cannot coexist because for one employer, the time when they were assigned to different departments overlap. So these two intervals overlap, so we cannot really have like three distinct values. So standard suggests that we have this additional keyword with no overlap. And then this is something which defines the primary key in temporal tables according to the standard. And then a standard defines integrity constraints or foreign keys pretty much the similar way. So when we say that, okay, there's like our child table and there's a parent table and there's referential integrity, we also include the intervals. So intervals should be overlapping. So then only then it makes sense. For queries and for data manipulation, standards extends syntax. So here are two examples, example of update and example of select. So when we update or insert or delete, we should define the interval to which we apply these values. And that's both for application time and system time. And similarly, when we query, we define what time period we are talking about in this query. So that is extended syntax again, which is approved by the standard. Now, Postgres. What does Postgres have? Because we are talking about Postgres. That's Postgres conference after all. So what Postgres have to support time? Why Mike Stonebreaker wants us to support? First of all, Postgres actually have period types. And you know what? Standard does not require, but also what standard says, if you have period, full speed ahead. And having period types makes lots of difference. I can tell you that makes life very much easier. And also we have all this rich set of operators and functions of timestamps, intervals, and periods. So we can implement all the time predicates, we can implement all the logic working in time. And all the predicates are implemented as required by standard. So it's a little bit different from Allen operators, but exactly how standard defines it. And we have open close, so pretty much we're good here. In addition, Postgres have gist indices, so just special indexes. And using gist indexes, you can define gist with exclusion constraint, which does exactly what standard asks us to do when we define primary key for temporal tables. So you have everything. You have everything except we do not have it, okay? So Postgres has all the apparatus which would make implementation of temporal standard easy. Just need to expand syntax. We need create table which defines it as temporal table. We need to extend select, and we need to extend data manipulation. So we have everything and we do not have it. So that's a problem, I think, that we need to address in Postgres. And like some of you know that I've been working on resolving this problem for a very, very long time. And the way how I was working on it, I introduced PG bitemporal. So that is supporting of two-dimensional time in Postgres. And I was always saying that is not by standard, that is asserted versioning model. But when I looked at the standard, I realized that actually we have most of the things which are required by standard. So now we want to run quick compare and see what we have and what we are still missing. So bitemporal model supports two application times according to the standard. One is assertive time and the other is effective time. So two time dimensions. Transactional dimension, which is required, it's not required. So standard says you can do either transactional or application or both. But we do not really have transactional dimension. However, it's very easily restored because it's implicitly defined. Each row has row created at timestamp, which allows us, if we want to, reconstruct this transactional time. Bitemporal model heavily relies on everything which Postgres have to offer. We use intervals, we use all these interval operators, we use gist with exclusion. That's how we define primary keys, that's how we define referential integrity constraints. In addition, we provide very detailed semantics of the ways how bitemporal update operations work. So we have update, correction, delete, and inactivate. And we have support of integrity constraints. So one more time about storage and indices. Bitemporal primary keys, or they are called business keys in PG bitemporal, are defined as a key, like actual database key, with no overlap because we use gist. So it's pretty much exactly what standard wants us to do. And also the presence of gist indices make bitemporal search very efficient. There is no need to have current in one table, archive in the other table. We can have everything in one and be very efficient querying both history and current status of data with no problem. So for queries, we do not have extension because PG bitemporal is not Postgres extension. So thereby we do not have syntax extension. So we have time-related conditions which have to be explicitly specified. Standard allows this. So when you write select, you need to tell where you want to stand for effective time, for asserted time. Then we can use all this built-in predicates, which are present in Postgres. But fully temporal queries are still tricky because the idea of fully temporal queries, you join one bitemporal table, the other bitemporal table, and as a result, you get another bitemporal table. So again, not the snapshot. Right now, we mostly do snapshots, but it's possible to produce bitemporal table, but it's not obvious. We do not have any special syntax for this. Then we implement all the DML operations. So we have bitemporal insert, update, correction, inactivate, and delete. And these distinctions are not clearly identified in the standard. And I think that people who wrote standard did not try to do it in practice. So we very, very, very carefully, precisely define what are the distinctions depending on what exactly we are modifying and what exactly we are deleting. Because, temporal database method does not disappear. You delete, but you do not really delete. And yeah, good luck with compliance, which requires you to delete something after a certain period of time. We cannot. All right, so to summarize, this table represents a comparison of bitemporal model versus SQL standard. So surprisingly, as you can see, there are more similarities than differences. So pretty much the difference we have is that we do not have explicit transactional time, and we do not have extended syntax. But everything else is in place. So we have user-defined functions for DML operations, but if somebody will be willing to make them look like normal updates and so deletes, I think it will be very cool. Okay. So what is still missing? So let's do one more sweep through all of what we just talked and just highlight what is missing. So what is missing in standard, by the way, because but we still want to live by the standard and we want to make sure that standard covers everything. Support of more than one application time and doing two-dimensional application time for very long time, I can tell you that future assertions are extremely helpful. Update versus correction distinction is extremely helpful, and this is not reflected in the standard. Period join, again, what I just said, full temporal join. So we join two tables and get a result as temporal table. That is not clearly defined in the standard also. So that's something which we probably want to do. And same applies to period aggregate support. So it's obvious that that is something which may be very helpful, and we do not have it defined in the standard. And since it's not defined, we cannot really implement it. So what is missing in Postgres? As I said, everything except actual temporal models, right? So there is no bitemporal, it's still just my library, and there is actually no SQL support of temporality in general, though so many people build their own applications where they support temporal tables. Like, it's not even funny. I think that we need to do something. And finally, what is missing in a temporal model? So mostly syntax extensions. I know that the user-defined functions are ugly, okay? So that's why people kind of reluctant to use them, because you need to write too much and it does not look pretty and it's difficult to embed it into applications. Design methodologies, they are not defined, by the way, neither in standards nor in bitemporal, because the question what should be considered, application time, what is effective, what is asserted, is design concept, and it's not always easy to identify. And explicit support of transaction time. So I kind of question that we really need it, because we don't really need it. But if we want to be like really like standard 7, follow the standard, we can construct the end of the transaction time, and we can like make bitemporal model to support transaction time. So that's it pretty much. So what we have in conclusion, the SQL standard provides a very like solid, sensible like foundation for developing temporal tables. And Postgres has everything to make it a reality. So we're waiting for somebody who will make it a reality. And I think that we implemented lots of this in PG bitemporal. So it's not as far from the standard as, again, as I used to say, and many people said to me. So I also think that there is some room for improvement, some room to work. So thank you so much. Thank you for listening. And please leave me some feedback. Leave me feedback on GitHub and leave me some feedback here. I would be curious to hear what you think. Thank you.